Thank you. Thank you, Anita. Thank you again for the invitation. So I'm going to continue my discussion of higher categories. And today I hope to tell you a bit about the applications in geometry and physics. Okay? So I'm going to go I'm going to wave my hands a bit about some of the technicalities having to do with higher categories. So far, I've been trying to give more or less precise definitions. We'll use those definitions, but I will need some more definitions, which I won't have time to elaborate on too much. So I will sort of wave my hands and say it works in a similar way to what we've already seen. Okay, so that's just inevitable. It takes thousands of pages to develop all this mathematics rigorously. So my goal is to sort of give you an idea how things work. So let's recall from last time, we talked about Siegel. We ended the discussion with discussion of Siegel-style definitions of categories. There's one small correction I have to make. I don't remember if I said this precisely. I have not watched the video, but in any case, I'm going to say it now. So let me just recall the definition. A Siegel category is given by a functor x from the simplex category delta op to spaces. So from now on, I think you've seen simplicial sets enough that I can say spaces is S set. Okay. You could also take spaces equal to top, but it just when you do this kind of homotopy theory, simplicial sets are a more convenient model often. So that's the reason. So a Siegel category is a functor like this, such that x0 is a set, is discrete. Okay, so it has no higher homotopy groups. To xn mapping to by the natural map to x1 plus x1 plus x1. And these are homotopy fiber products, and they're taken over x0. These are equivalences. And we saw, okay, so this is a Siegel category, the definition of a Siegel category. And in the interpretation of the structure is that x0 is thought of as a set of objects. So x dot defines an infinity category, x script x, where x0 is objects of x, x1 is the arrows, the space of arrows of x, and more specifically for x, y in x0, the mapping space xy, this is now a space, and this is the fiber product x cross over x0, x1. Right, so you take the source and target maps from x1 to x0. There are two phase maps. Those give you the two maps from x1 to x0. I hope it's clear which are the products. The products are the ones that have an h on top of them. So, and the others are x's. So this was the mapping space, and composition was given by looking at this. So it's not really a map from x1. You take two composable arrows. You would like to define a map that gives the product of those two arrows. There isn't such a map, but it's only well defined up in the homotopy category. So this map is composition is well defined. It's a well defined map only in the homotopy category of spaces. So spaces after inverting the equivalences, because you want to invert the left pointing arrow so that you can compose the inverse of the left pointing arrow with the forward pointing arrow. But that inverse only exists when you formally invert weak homotopy equivalences. So that was the idea. And the two comments, observations, that we made is that one is that if X is a complete Siegel space, let me write it like this. Let me say script X is just notation for X. Is a complete Siegel, sorry, is a Siegel category. Oh, so by the way, I should say Siegel categories were not quite defined by Siegel. They're based on Siegel's model for delooping, Siegel's delooping machine. But I guess these were defined. It's definitely there in work of Hirschowitz, Simpson, and similar ideas in works of Thamsamani in the 90s. Okay, so the observation is that first of all, if this is a Siegel category, then you can construct from it this thing I call pi 0 of X, which is a category. So sometimes it's also denoted the homotopy category of X, OX, and called the homotopy category. Of X, which is an ordinary category. So we get a good old category starting from a Siegel category. Basically, what we do is we take the mapping spaces and take the connected components of that. So we identify two one morphisms if there is a two morphism that identifies them. It's an isomorphism between them. The second thing is that if you have an ordinary category, then you get one of these guys. So if C is a category, then you can define. You get this thing called the nerve of C, which is a functor from delta op to simplicial sets. It's defined as delta op to sets. But every set can be thought of as a discrete simplicial set, which has, every set can be thought of as a constant simplicial set, where at every n you have the same set. X naught, right? So you can think of every set as just a discrete simplicial set, and therefore I can think of this as a functor from delta op to simplicial sets. And what is this functor? It's defined as follows: nc of n is just functors from n to c, and the functoriality is given by pulling back along. If you have a map from m to n, then you can just pull back along that to get this thing. So it's just Hom in cat from n to black. So this is called the nerve, and here's a fun exercise. You can characterize which simplicial sets arise. Sorry, exercise. You can characterize which simplicial sets arise as nerves as follows. So X from delta op to set is the nerve of a category. This is called the nerve. Is the nerve of a category if and only if it satisfies the Siegel condition. So if and only if Xn is isomorphic. Now these are sets, so you want this to be an isomorphism of sets, which is the same thing as the weak homotopy equivalence of sets. And they're discrete, there are no higher homotopy groups, so it's really the same thing. For all n. Okay. So in fact, we've seen that from a topological space, you can produce a simplicial set. So simplicial sets model topological spaces in that sense. But simplicial sets can also be used to model categories because you have a fully faithful functor from cat. So corollary is that cat sits inside simplicial sets with essential image. This is fully faithful. With essential image given by the exercise. So simplicial sets are a really powerful and flexible tool because they simultaneously model both of these things. And how do you prove? How do you go about proving this? Doing this exercise, you just use the ideas that we used when we talked about Siegel spaces, right? So if the maps from Xn to the fiber products are isomorphisms, then this map from X2 to X1 fiber product X1 X0 X1, this map is an isomorphism of sets, and so I can invert it. And when I invert it, I get a composition law from X1 across X1 over X0 to X1. I get a well-defined map in the category of sets, which is my composition, which literally is my composition. And then I should check it's associative, and for that I should use X3 as I did in the first lecture, and so on. So it's a straightforward exercise using the tools that we have developed so far. And it's also conceptually very important because every category can be thought of as simplicial this thing as a Siegel space. Now we can take this further. In fact, we can take this further. So if C is a simplicity enriched category, if C is an S set enriched category, and remember I said that that's one way to think about what an infinity category is, because the Homs are simplicial sets, and every simplicial set you can replace by a Kahn complex. It's weakly equivalent to Kahn complex, and that Kahn complex is an infinity groupoid. So you can think of it as having objects, paths between them, isomorphisms between parts, and so on, and it encodes the composition implicitly. So the simplicial set structure encodes the Kahn condition, encodes the composition of parts implicitly. So you can think of this as something where there are objects, and then there's an infinity groupoid of maps between them, which is the same thing as saying you have an infinity category with every morphism invertible above level 1. One morphisms need not be invertible, but everything is invertible above level 1. Now, suppose I have one of these things, I can define its node. And now it's really a functor from delta op to simplicial sets. And it sends n to maps, if you like, or functors maps from n to C in the category of simplicity in this LW cat set. So we take simplicial categories, and between any two simplicial categories, we have a set of maps between them, which forms a space, because we saw earlier that we can take simplicially enriched categories and invert Dwyer-Kahn equivalences. So these are the Dwyer-Kahn equivalences. If I invert those, I get a space of maps between two simplicity enriched categories. And we just saw that every category can be thought of as a simplicity, I mean, we didn't see that's immediate. Every category can be thought of as a simplicity enriched category. So I simply think of N, the category generated by this graph, as a simplicity enriched category where the Homs are discrete. And now I can look at its mapping space into any simplicity enriched category, and that defines its nerve. And this nerve of C is a Siegel category. It satisfies the Siegel axioms just like before. I mean, just like for categories in this exercise, I asked you to prove this. You see the same thing is true for Siegel categories. So you can go from simplicity enriched categories to this, which have strictly associative composition, to this thing that has a weaker composition. And in fact, these are all equivalences of homotopy theories. There's yet another way to model things called complete Siegel spaces, which is the one that is convenient in many ways for something that I'm going to talk about. So I'm just going to quickly mention this. Let me give a definition. X dot simplicial object from delta op to simplicial sets is a complete Siegel space. Oops, I should highlight this probably. Is a complete Siegel space if it satisfies the Siegel condition. So same as before. So I haven't changed this. But what I'm going to change is that I'm going to ask that I'm going to drop the condition that x naught is a set. So instead of x naught instead of x0 representing the set of objects, it's going to represent the infinity groupoid that I get by discarding all non-invertible morphisms in my infinity one category. So imagine I have some infinity one category. It has objects, one morphisms, and so on, two morphisms, and so on. So it has objects, and for every two objects, it has an infinity groupoid of maps between them. Now imagine that I just throw away all the maps, all the one morphisms that are not invertible. So then I have, the resulting structure is a higher category, an infinity category, in which every map is invertible up to homotopy. So it itself is an infinity groupoid, and so it's represented by a space. So x naught is going to represent that space. But I need to make sure that this space x naught, which represents an infinity groupoid, is the same infinity groupoid as what I get if I use the Siegel axioms to construct a multiplication on the one morphisms. So I'm going to encode that by saying that x naught mapping by the degeneracy map s naught to x1 induces an equivalence, in weak homotopy equivalence, of x naught to x1 invertible, where x1 invertible consists of all one morphisms that are invertible. So where x1 invertible contained in x1 is the union of all connected components such that for f belonging to x1, the equivalence class of f in pi naught of x1 is invertible as an arrow in the homotopy category, pi naught of x. Right? So every arrow defines an arrow, every point in x1 defines an arrow in the homotopy category. It also defines an arrow in the infinity category, but defines an arrow in the homotopy category. I want that arrow to be invertible. If that happens, I say that my arrow in x1, my point in x1, which represents an arrow, lies in this connected component x1 invertible. Because x1 invertible is characterized by this property. And I want the degeneracy map to induce an equivalence of objects with all invertible arrows. The space of objects with all invertible arrows. So this encodes that the two ways of thinking about invertible arrows would be consistent. I can either think of an invertible arrow as a path in x naught, which is my infinity groupoid, or I can think of it as an element of x1. And I want those two things to agree, and that's what this axiom does for you. Okay. So we have seen several models for ways to model. We've seen several ways to model the idea of an infinity one category. So let's list some of them quickly. So we had S-set enriched categories. I could also do top enriched categories. Here we have A infinity categories. We have quasi categories. We have complete Siegel spaces. We have Siegel categories. These are the ones we have seen so far, and there are more. And the theorem, the big sort of theorem in this field. So in the beginning of higher category theory, it wasn't clear how to make the idea of a higher category precise. There were all these different ways of thinking about it. And it's not, a priori wasn't even clear how do you compare them. You need a common framework in which to say that this way of thinking about infinity categories is the same as the other way. So you have to ask, what do infinity categories themselves form? And they themselves form an infinity category. In fact, they form something called an infinity 2 category, but in particular, they form an infinity 1 category. And so you want to say that all of these are equivalent. So the infinity category of S set enriched categories is equivalent to the infinity category of A infinity categories, is equivalent to the infinity category of quasi categories, and so on. To make this statement, I have to choose one model for infinity categories that I like or I find convenient, and use that to formulate the sentence, the infinity category of blank, right? So suppose I take my definition of infinity categories to be S set enriched categories. Then I would like to say the S set enriched category of simplistic set enriched categories is equivalent to the simplistic set enriched category of A infinity categories, is equivalent to the simplistic set enriched category of quasi categories, and so on. And we also saw that you get an S set enriched category from a relative category, from a pair C, W by simplicial localization. So another way to say it is I could organize each of these into relative categories and then say, are they equivalent after simplicial localization, right? So the statement is really that each of these, so in fact, I could add relative categories as another model here. So these are just pairs C, W, where C and W are ordinary categories. So each of these can be organized into a relative category. And the simplicial localizations are all equivalent. Of these are equivalent. So this is, I guess, due to several people, maybe Bergner, Lurie, etc., 2000s. Okay, and so let me just, I think I've mentioned some of these things. I've said these along the way in the talks, but let me just say what the weak equivalences are in each case. So for S set enriched categories, there would be Dwyer-Kahn equivalences. For A infinity categories, there would be also something like Dwyer-Kahn equivalences. They're usually not called that, but we can call them that. For quasi categories, there's a construction called the simplicial nerve, which, there's an adjunction between quasi categories and simplicially enriched categories, which takes a quasi category and produces a simplicity enriched category. And you say that two quasi categories are weakly equivalent if the corresponding simplicity enriched categories are weakly equivalent. That's one way to define it. For complete Siegel spaces, they're the nicest because the nicest from this point of view, because a weak equivalence of complete Siegel spaces is simply a level-wise equivalence of the simplicial objects, right? So if X and X prime are two complete Siegel spaces, a weak equivalence is simply a map that is an isomorphism that's weak equivalence at each level. So maybe I should write this here. Weak equivalences for complete Siegel spaces are just maps f x dot to x prime dot such that fn from xn to xn prime is a weak commutative equivalence of spaces for all n. Okay. So this is somehow, from this point of view, it's very nice. Complete Siegel spaces are very nice because the weak equivalents are easy to understand. And for relative categories, again, you can take the simplicial localizations and ask for those to be Dwyer-Kahn equivalent. That's one definition. So essentially all these ways of thinking, so this theorem guarantees you, and by the way, if you look in the literature, usually this is stated in the language of model categories. And model categories are basically relative categories or homotopy theories. I think I call them homotopy theories. Okay, anyway, let me just say aka homotopy theories. That's legible. So basically all these different ways of thinking about higher categories are equivalent, and that's on firm mathematical footing once you choose the framework in which you want to compare them, right? And it's sort of independent of the framework because I could use any other definition of infinity category as a common framework in which to compare them, and I would get the same result. So, okay. Okay, great. So that's about infinity categories. So I mean, now again, go back to slightly heuristic mode. Heuristic definition, which I gave last time, but I just want to recall it. So an infinity n category is a higher category with morphisms for all n, for all k, zero, such that k morphisms are invertible for k bigger than n. So the simplest example would be just a two category. Bicategories. These are things that have, they're defined by category B is defined by giving objects a set and then for all xy in objects of B, you want some B of xy, a category, and for all xyz, you want functors B of yz cross B of xz to be of, oops, sorry, xy. B of xz, let's call this multiplication. Let me write it like this. Let me write this is fg goes to f circle g at the level of objects and then at the level of morphisms as well. So let me call this map circle. So it's a functor. So it acts on the objects of B of xy and B of yz. It also acts on the morphisms between these objects. Plus data, well, maybe I should call it some capital. It's a good notation here, maybe. Sure. Yeah, I think this is fine. And then you want natural transformations alpha should write it. You want natural identifications, blank circle blank circle blank alpha to blank circle blank circle blank. What I mean by this is that you have alpha FGH, which goes from F circle G circle H, natural transformations which are invertible, so natural isomorphisms. To F circle G circle H. So you have these maps satisfying various satisfying, oh, sorry, I should say units. Unit objects 1x in Bxx, satisfying various things, satisfying coherence conditions. And let me just write down to give you a flavor, the coherence condition involving alpha is that if you had four things, F, G, H, and K, then you would have all these ways of bracketing. So you'd have F composed G, composed H, composed K. And all these things should be, this diagram should should commute. So you should have what I get F circle G circle H circle K. Then I should have here. So I want to go from. So I want to do F circle G circle H. Okay. So this pentagon should be commutative. So the alphas, you can figure out the direction of the alphas. I'm not going to write it out, but these maps are given by alphas, and you want this diagram to commute. So this is sort of the key type of axiom you want. And then, there's things for units and so on. I won't write all of them down. There's sort of self-explanatory. You can construct the definition from what you should expect. But this is the key axiom. Okay. So let me just give you examples of these bicategories. So one is that a bicategory with one object star is the same thing as what people call a monoidal category. Let's call this monoidal category V, which is equal to B of star star. And you have a map tensor, which is my composition, mapping V tensor V, so V cross V to V. And the axioms are exactly the axioms of a monoidal category. So monoidal category is nothing but a bicategory with one object. Here's a more fun example. I mean, well, this is also fun, but here's a nice example. A very important one. This is called Morita theory, Morita bicategory. So you can take the objects to be, so fix some field, let's call this alg, Morita bicategory alg K, where K is some field. You can do rings and so on. So the objects of B are algebras over K. And B of A, comma B is the category of AB bimodules. And composition from B of BC cross B. Composition is tensor, and composition is given by this takes M, which is a bimodule, and N, which is an AB bimodule, and sends it to, maybe I didn't write it in the optimal order, but okay, N tensor B. Okay, so this is a very important example of a bicategory. You can also construct bicategories from any category by taking correspondences in that category. So if you have, correspondence categories, which is very closely related to Morita theory. So if C is a category with products, then you can take this gives rise to some correspondences in C by category. The objects of correspondences of C are the objects of C, and Hom, so correspondences of C from X to Y is basically maps to X cross Y, or actually I didn't have to say with products, I guess, maybe not. So these are maps Z to X cross Y. In other words, you can think of it as a kind of roof sitting over X and Y. And composition is given, I think I want category with fiber products. And composition is given by Filbert. So composition is this. And so I said the category of maps between X and Y. I just wrote this diagram here, but more precisely, I should say it's the over category. Is this is the category? This is a category correspondence of CX to Y, and it's the category C over X cross Y. So the objects of this category are diagrams Z to X cross Y and Hom Z to Z prime, where Z and Z prime are such diagrams, is, well, it's what you think it is. So it's two diagrams, commutative diagrams. Commutative diagrams. Z. So you have to provide the F. Okay. So that's an important example. Okay, so these are all bi-categories, and you could do the same. The last construction I did, you could do it with an infinity 1 category, and you would get what's, at least heuristically. So I haven't defined yet an infinity 2 category, but let me just say heuristically. Let's give some examples in the infinity world. Okay, so first let's give some examples of infinity 1 categories, and let's see how to manufacture infinity 2 categories of those. And then I'm going to apply this to later in topological field theory. So let's do some more examples of infinity 1 categories. Now I'm going to give you some examples coming from geometry and physics. So we saw that anytime you have a category in weak equivalences, you can localize and get an infinity 1 category. So if A is in your abelian category, then you can form chain complexes of A with quasi-isomorphisms. These are quasi-isomorphisms. These are chain complexes of objects in A. And if you don't know what an abelian category is, just think of R modules. That's fine. That's a perfectly good example. I'll give those sub-examples in a moment. So this gives rise to an infinity category LW CH of A, which is often also denoted D of A. And it's called the derived category of A. This is the derived infinity category of A. Or simply the derived category. Okay. So sub-examples would be, you could take A equal to R modules, R some ring, and this gives rise to the derived category of R. And this is called the derived category of R modules. You could also take a more global geometric version of this. You could take A to be coherent sheaves on some scheme. Again, if you've not seen coherent sheaves before, you can think of these as like some generalization of vector bundles, holomorphic vector bundles on a complex manifold. On a scheme X, then, oh, sorry, okay, let me take quasi-coherent sheaves. So this gives rise to D of A is D Qco of X, the derived category of quasi-coherent sheaves. So this is the in the special case where you have an affine scheme, then it's just the previous case where I talked about R modules. Okay, so this is coming from geometry. So in geometry, you have this natural category. So this is, you could do 2 prime, which is you could take A to be coherent sheaves on X. And that gives rise to derived category of coherent sheaves, which some other category you can associate. Okay, so so this is from algebraic geometry. So let me now give some examples coming from. Okay, so I wanted to give a symplectic example, but I just want to say make a comment here. So you might wonder. So I've defined derived category of a scheme, and I've defined this big category. Now you can ask, how far is it from being from being modules over something? And in fact, for any reasonable space, it's always modules over an associative algebra, associative DG algebra. So in if you're willing to work with non-commutative algebras, then every scheme is affine. That's the conclusion of this statement. So let me just say what the theorem is. So make a definition and then state a theorem. So definition is that an object E in, so okay, let X be an E. I'm going to use some words that maybe I have not introduced, but you can just ignore those and just sort of take the basic idea of this statement. Let X be a triangulated infinity category, also known as a stable infinity category. Okay, maybe just say stable infinity category. Let X be a stable, this is an adjective I've not introduced, infinity category with all colimits, with all homotopy colimits. So what you need to know is that examples of these are the ones I gave above. So examples D of R, D of Q co of X. Then an object E in X is compact if Hom or maps from E to blank commutes with filtered colimits. So this says that E is small in some sense. It's compact because when you map it into something, a very large colimit, a filtered colimit, you can think of as some kind of large union. If you haven't seen this before, you can think of it as some union, and it basically means that if you map into the union, you land inside some element of this union. Okay, so that's roughly what it means. But the formal definition is what I've written. It commutes with filtered colimits. And 2, it's a generator if map EF is contractible for all F implies that sorry, what am I saying? Map EF is contractible implies that F is 0. F is the 0 object. So a stable infinity category has something called a 0 object. It's like an abelian category in the world of infinity categories. And all of these examples I gave you are of that type because they came as derived categories of abelian categories. So whatever that means, it has something called a 0 object. And basically, the first axiom says that E is small in the sense that I defined, I just described. And the second axiom says that E is big enough to detect any object. So if E maps an E to some object as 0, then that object is trivial. Okay, and so the theorem due to Bondal-Vandenberg. Okay, so actually before I state the theorem, maybe let me state a fact, an exercise maybe even, if you know what these words mean, is if you know what stable infinity category is, then you can, or if you just read the definition, you can attempt this exercise. It says that if E is a compact generator, then maps from E to blank, well, this defines a functor from X to modules over A, to the derived category of modules over, or derived category of mod A, where I could just write mod A, but A is going to be a DG algebra, where with sense F goes to maps from E to F, which is acted on by A, which is maps from E to E, which is going to be an A infinity algebra, or this is an A infinity algebra. Right? Because it's the endomorphisms of an object in an infinity category, so it's a space with a multiplication. Or if I was working in a linear setting like I am here, then I can think of it as a chain complex with a multiplication. Okay, so maybe I should just remark in the two examples that I gave, if we are working, oops, sorry, if we work over field K, then D of R and D of Q of X are K-linear categories, K-linear infinity categories. And one model for this, so now I hope I've made it clear by now what it means to say you have a model for something. It means you have one way to systematically think about the idea of that thing. I mean, so you're talking about infinity categories. Complete single spaces are a model for the idea of an infinity category. So I'm going to give you a model for what it means to have a K-linear infinity category. Here's one way to model it. That is simply a category enriched in chain complexes. So model for K-linear infinity category, whatever this means, you can take the following as a definition, is that is differential graded categories which are categories enriched in chain complexes. So this means you have objects. So if X is a DG category, then you have objects of X as a set. And for all XY in objects of X, you have some map underlying XY, which is a chain complex. And composition is given by a map from composition is a map. Maps YZ, tensor maps XY, maps XZ, strictly associative. And you can, of course, relax the associativity like I did in the first lecture and work with A infinity categories where associativity is only up to homotopy. And it turns out every A infinity category can be strictified and made into a thing where you have strict associativity, which is a DG category. So that's a theorem that works for A infinity category, for infinity one categories. Anyway, so in this case, so example of this would be DG category with one object. One object is the same thing as a DG algebra. That's a definition, if you like. But it's the same thing as giving a chain complex with a multiplication. So that's the same as giving a chain complex with a map from A tensor AI to AJ to AI plus J, multiplication maps, and a differential D from AI to AI plus 1, such that D of A times B is dA times B plus minus 1 to A times dB. That's equivalent to what this is kind of the structure that you get if you write out this definition. Okay, so that's what a DG algebra is. And the upshot is that if E is a compact generator, well, if E is any object, is an object in a k-linear infinity category, X, in other words, a DG category, then map underline in X from E to E is a DG algebra. It's basically a subcategory consisting of one object, so it's a DG algebra. So if I go back here, I have this A infinity algebra or DG algebra. And the exercise is to say that this functor from X to derived category of modules over A is an equivalence if E is a compact generator. I already wrote that. Right? So if you have a compact generator, then this map is an equivalence. So you can think of the category as just the category of modules over the endomorphisms of the compact generator. And in fact, all the categories that arise in geometry, the ones that I wrote down, have this property. So theorem.
I have a small doubt.
Yeah.
Yeah. So in this case, when you write map underline, so here you mean the maps in the stable category, which is factored by the injective or projective.
No. Stable I'm using in a different sense. I'm using in the sense of triangulated. So
Okay.
You're thinking of like
stable category of an exact category in the sense of Euler. So it's
not, it's not the same use of the word stable, although the category that you're constructing can also be promoted. So the stable category that you construct, if you do it in a refined way, you can actually produce a stable infinity category. But the use of the adjective stable in your definition has to do with something different from
even for the DG categories or the DG algebras which you have mentioned.
I mean, I'm saying that you're using the word stable to indicate something else, although we are both talking about an example of what's called a stable infinity category. So maybe I should, if people, here I'm using stable in the sense of triangulated. So stable means triangulated.
Okay.
And your construction does produce a triangulated infinity category. I mean, the right name for that is stable infinity category. But in your setting, the word stable is used to mean something else. So it's kind of unrelated.
Okay, I see. Thanks.
I hope that it's a little confusing, but a stable category is one source of stable infinity categories. Okay, let's put it that way. Abelian categories are a source. You start with an exact category and you pass to the stable category. You get one way to construct these kind of objects. If you just do what you normally naively do in representation theory, you would get the homotopy category of the infinity category that I'm talking about. You get pi naught of it. That's what people usually wrote down earlier. But over time, it's become clear that working with that pi naught is like, it doesn't have enough information to do various things that you would like to do, which I don't have time to tell you about all of that. But yeah. Did that clarify things? I mean, this means triangulated. Okay, so for me, stable means triangulated.
Thanks.
So maybe for those who have seen this sort of stuff before, I'll just say what stable is in two or three words. An infinity category is stable if it has a zero object, which means that an object such that it is both homotopy initial and homotopy final. Maps from anything into it is contractible, and maps from it to anything is contractible. That's a zero object. So it has a zero object. It has finite homotopy limits and homotopy colimits, finite homotopy limits and homotopy colimits. And pullback squares agree with pushout squares. Every pullback square is a pushout square and vice versa. So in particular, you have pullback pushout squares of this form, of the form x, y, z, 0. These are both pullback and pushout squares simultaneously by definition of stable infinity category. And such squares are called triangles. So x, y, z is called an exact triangle. So the homotopy category of any stable infinity category is triangulated. And that's the reason why stable infinity categories are important. But triangulated categories are kind of deficient because being triangulated is an extra structure on a category, but being stable is a property. I just defined the property of an infinity category to be stable, which makes it nice in many ways because you don't have to prescribe what the triangles are. They're sort of characterized by a universal property, namely being a push-out square. So that makes everything nice, much nicer. Okay, so moving on. So there's a theorem of Bondar-Vandenberg that says that if X is a quasi-compact, quasi-separated scheme, then D quasi-coherent of X admits a compact generator. So if you care only about the derived category, if you only see geometry through the eyes of the derived category, then every scheme is non-commutative affine, can be viewed as a DG affine scheme, if you allow associative but not commutative rings. That's what this says morally. Okay, so let me just give, let me state another theorem here. These theorems are kind of really big theorems, and I think I can't prove any of them in the course of these lectures because each of them requires some time to develop, but they're really the cornerstones of this whole theory. So let me just state this theorem of Thorn, Morita theory, which will connect the things I said before. So this theorem says that if you have two DG categories, C and D, or X and Y, let's say, I used X and Y DG categories with all colimits. I'm going to paraphrase and state it a bit vaguely, and I won't state all the technical hypotheses. Okay, so with homotopy colimits, which are presentable, which means that let me state a special case of Thorn's theorem. So with all homotopy colimits admitting compact generators, E and F respectively. So then we have let A be maps X from E to E, and let B be maps F. Then we know that we have X is equivalent to derived category of A modules, and Y is equivalent to derived category B modules. And you can look at continuous functors. So continuous functors, which means that preserving colimits from X to Y. Well, this is equivalent to the derived category of AB by modules. So one way to think of the collection of all big DG categories, which have all homotopy colimits and continuous functors between them, is to think of the Morita category of DG algebras and bimodules between them. It's another way to model the same thing. So in particular, if you want to understand functors between schemes, so in particular, continuous functors from D quasi-coherent of X to D quasi-coherent of Y, XY schemes, let's say nice schemes, quasi-compact, quasi-square, whatever. So this is equivalent to D quasi-coherent of X cross Y. Right? This is Morita theory, and so here, what is the identification here? Given a bimodule M, I get a functor which sends. So M gives a functor phi M from mod A to mod B, or whatever derived category. I should just say mod A actually, but anyway, let's say derived. So phi m of some module, phi m of n is n tensor. So so that's the functor, and well, I shouldn't say in particular here. This is kind of a corollary. So I mean, it requires a little bit of work. Let's say corollary. Okay, and what is the correspondence if you have some sheaf f in some complex of sheaves in D quasi-coherent of x cross y? You get this functor from phi sub f, let's say, from D quasi-coherent of x to D quasi-coherent of y, which is defined by phi sub f of some sheaf, complex of sheaves E is pi 1 upper star of E, where pi 1 is a projection from x plus y to x, and pi 2 is the projection from x plus y to y. So pi 1 upper star of E, you take the derived tensor product with f, and then you push forward along. So everything is derived. So I should say L pi 2 lower star. So all functors are derived functors. Right. So this is the correspondence, and it tells you that you can think of maps between the categories as being given by correspondences, basically, by objects living on x cross y. So those two examples I gave are really important in understanding geometry, and this thing is called Fourier-Mukai theorem. So people study this. Okay, so we have these nice examples. Let me give you one last example, which I will just completely wave my hands about. Example is if x omega, so maybe I should give a definition. I don't know if people know what a symplectic manifold is. A symplectic manifold is given by is a pair M omega, where M is a smooth real manifold, is a real manifold. It has to be of even dimension, it will turn out. Let me just say of dimension 2n. I don't have to assume this, it will be a consequence of the definition that it has to be of even dimension. Omega is a two form. Which is non-degenerate. Which means that omega b blank from at any point from Tp of m to T dual P of m is an iso. And d omega is 0. That's what a symplectic manifold is. So an example is any cotangent bundle, for example, is a symplectic manifold to the standard symplectic structure. And if you have a symplectic manifold, you get, you can talk about Lagrangian submanifolds. So let me say example. So one example would be T dual of n for any manifold n, and locally, if you have x1 through xn coordinates on n, then and p1 through pn induced coordinates on the cotangent fibers, then omega is just summation dxi with dpi. So that's one example. Another example is any projective variety with the any smooth projective variety over C with the induced with omega induced by the Fubini-Study metric. On P and C. Okay, so I'm not going to have time to define this. And if you have a symplectic manifold, you can make this definition, which is that you say that L contained in M submanifold is Lagrangian if L restricted to omega restricted to L is 0 and dimension of L is half the dimension of M. Okay. So these Lagrangian submanifolds play a very important role in the study of symplectic manifolds. They are sort of like, you know, if you think of the case of a cotangent bundle like R2n with coordinates x1, x and p, then the idea is somehow that in quantum mechanics, if you kind of localize, you can never localize the particle exactly. If you specify the positions exactly, then the momenta are completely unknown and vice versa. And the p's play the role of momenta, the x's play the role of positions here. So if you localize, if you fix x's, then you get arbitrary p, so that's one Lagrangian submanifold. If you fix p's, you get arbitrary x, that's another example of Lagrangian submanifold. But in general, you can have some mix of the two, some mix of things. And that's one way to think about, you know, why you might care about Lagrangians. So if M omega is symplectic, then this gives rise to this thing called the Fukaya category of M omega, which is an A infinity category. So it's a model for an infinity 1 category, linear over something called the Novikov ring. Okay, so K, so C. Okay, but then never mind, the CTR thing, it's linear over some funky ring, and it's called the Fukaya category. And what are the objects? The objects of Fukaya of M omega. So it takes, again, to give a very precise definition, it takes hundreds of pages of mathematics. I'm not going to do that here, but I'm just going to give you the idea. The objects are decorated Lagrangian submanifolds. And I won't tell you what the decoration is. So you can think of them as just Lagrangian submanifolds. And I have to tell you what the Hom maps from L1 to L2 to Lagrangians. This is, as a graded vector space, is the direct sum over C times P. P belongs to L1 and intersect L2. So it's a sum over the intersection points. And the differential is given by counting pseudo-holomorphic disks with boundary on L2. So you count disks whose boundaries are on these things, and the differential. So if you want to calculate the differential, let's say P and Q are these two intersection points, you want to calculate D of P. It's going to be some sum of things C P Q times Q. Now the coefficient of Q in this list is given by counting these disks which span whose boundary lies on L1 and L2. L1 and L2. Okay, so it's some category you can build from symplectic geometry. Okay, so now here's I promised a bit of physics, so let me tell you a punchline that comes. Oops, I'm not able to go on to the next page. Oh, okay. So here's a very deep statement that comes from physics, and then I'll try to tell you how higher category theory helps you explain the statement. So mirror symmetry was this very strange prediction by physicists that if you look at what are called Calabi-Yau manifolds, right? So these are complex manifolds that also have a symplectic structure, which is compatible in some way. So these are called Kähler manifolds. So what they predicted was that if you look at Calabi-Yau Kähler manifolds, they occur more or less in some kind of pairs, where for a given geometry, of a given Calabi-Yau manifold, you can find a dual Calabi-Yau manifold called the mirror, in such a way that the algebraic geometry of the first Calabi-Yau, the complex geometry of the first manifold, is encoded in the symplectic geometry of the second manifold, and vice versa. Okay, so mirror symmetry predicted this duality, and Kontsevich, formulated this thing called homological mirror symmetry. So before he formulated this, what physicists had done was to say that there were these very hard enumerative geometry problems. So you can ask, for example, you take something like the quintic. Okay, so maybe before I do this homological mirror symmetry, I just want to say, you could take something like, an example would be you take z0 to the 5 plus z1 to the 5 plus z5 to the 5. You look at the zeros of this contained inside P4. Okay. This is a three-dimensional Calabi-Yau manifold. It's something very explicit I wrote down, and you can ask questions like how many lines are there on this space, and you can count it exactly in this 2875 lines, and you can ask how many degree 2 curves live on this space, and you can count those exactly, and so on. But the numbers grow very, very fast, and they become astronomical, and also it's very difficult to even how do you even know that there are only finitely many as you increase the degree of the curve, and so on. So there were these conjectures about the existence of finitely many curves of a given degree, and also about formulas for, there was a program to try and understand what these numbers were. And physicists were able to predict these numbers in the early 90s by using mirror symmetry. So they said that given this Calabi-Yau manifold here, we can construct this dual space such that the symplectic geometry of that dual space is the algebraic geometry of this space, and vice versa. And they were able to use algebraic geometry on one side, where you can write polynomials and compute things explicitly, to predict, to say what the number of curves is on the other side, right? So it's a very highly non-trivial prediction, but there was no systematic way to understand. And so what Kontsevich did is he proposed the following thing. He proposed a program called homological mirror symmetry, where you make the following definition. You say that a Kähler manifold, so let x, not let, sorry, sort of definition, x omega I, so x omega is a symplectic manifold, xi is a complex manifold, is homologically mirror to x check omega check I check if the Fukaya category, which is an A-infinity category, this was in 1994, and at that time things were not even, Fukaya category had not even been developed and fully defined completely. So it was a huge leap of imagination to think up this explanation for the phenomenon that physicists had observed. The Fukaya category of x omega is equivalent to the derived category of coherent sheaves on X check the complex structure I check, and the derived category of coherent sheaves on Xi is equivalent to Fukaya category of X omega. So this is HMS. So this is called HMS, homological mirror symmetry, it's just an abbreviation. So this is HMS for Calabi-Yau. X omega I, X check, omega check, I check. And there are generalizations to the non-Calabi-Yau case. Okay. So these are supposed to be equivalences of A infinity categories. So he came up with this conjecture, and now you can ask, well, how can you recover things like curve counts, which is what people cared about? How can you recover it from homological mirror symmetry? That's one question. Also, you could ask, how is this related to physics? I mean, physics predicted this, and this is some very abstract stuff about infinity categories. So really, in retrospect, can you understand it in terms of physics? So it turns out that the objects in these categories can be interpreted as what are called branes in physics, but branes had not been discovered or had not played an important role in physics at the time when Kontsevich made this conjecture. So around the time that Kontsevich made this conjecture, physicists discovered these objects called branes in string theory, and the branes turn out to be the objects in these categories. So sometimes Fukaya categories are called categories of A branes, and derived categories of coherent sheaves are called categories of B branes.
I'm sorry.
Yeah.
So what was the definition and what was the statement? So the definition is homologically mirrored to.
Yeah, this is definition. Yeah. And now the exhortation is that anytime you have a Calabi-Yau, you should look for another Calabi-Yau. You should find a systematic way to construct a dual Calabi-Yau and prove that the dual Calabi-Yau is homologically mirrored in the sense of this definition. So there are prescriptions called SYZ. There are many prescriptions actually. There's one called SYZ mirror symmetry, which tells you that if you're given a Calabi-Yau X manifold X equipped with a certain kind of fibration, you can construct a dual fibration, and then you can ask, is that dual fibration object, the dual manifold, is that homologically mirrored in the sense of this definition? So the conjecture is that it is homologically mirrored, and there's a program to prove it.
Okay, so the whole thing is still a conjecture.
Well, yes, it is a conjecture in very, okay, it depends what context you ask me that question, right? So if you ask me for a specific example, like for this manifold, is it mirror to this other manifold? In the initial days of homological mirror symmetry, people proved it in examples. They took examples and proved this manifold is which was believed by physicists to be mirror to some other manifold.
Okay.
It was just a belief in physics, right? Based on some physical heuristics. How do we even make a mathematical statement out of it? So this is the mathematical statement, one possible mathematical statement, that they are homologically mirrored. And then people proved, for example, by example, that these are homologically mirrored. That's the first phase of this kind of evolution. Then people came up with a program to say, given a manifold of a certain type, like a toric variety or complete intersection in a toric variety, here's a combinatorial prescription to construct another manifold, which is conjecturally the homological mirror. And now there's an entire program to prove that this is homologically mirrored. So to say that it's just a conjecture, I mean, it's kind of like, it's not black and white. I mean, there's a whole program, just like the Langlands program is a program that took, you can say Langlands program is a conjecture. Yes, it is a conjecture, but there's huge amounts of work that have been done on it. And it's a whole field, right? I mean, it's not a small question that can be answered in one paper or something. I mean, so there are entire programs to try and prove that various prescriptions for mirror manifold construction are actually homologically mirror in the sense that I just defined. I mean, give you homological mirrors. Did that answer the question?
Yes, thanks.
Yeah. Okay. So maybe just really quickly in the last 10 minutes, let me just explain where this comes out of. This comes out of physics, and I just want to explain it, and also a very deep piece of mathematics that really uses the power of higher category theory. Okay, so I want to talk about topological quantum field theories. So topological quantum field theories are these things that Okay, so quantum field theories are things that govern essentially all of modern physics. Quantum field theories, are the language of modern physics, but they remain out of reach of rigorous mathematics in most cases, right? Because to define in the modern point of view on quantum field theory involves something called the path integral, and that's an integral over an infinite dimensional space. And the measure on that space is not mathematically rigorously defined. So it's a bit like how people did Lebesgue integration before, people did integration before Lebesgue and proved various things, but they didn't have the rigorous definition of a Lebesgue integral in, people like Fourier and so on. And we're at that stage, or maybe even earlier than that stage, when it comes to understanding what physicists are calculating, because they're integrating over infinite dimensional spaces. But there are special cases where you can axiomatize the properties of what you get from doing the path integral, which is this infinite dimensional integral. And topological quantum field theories are an example of that. So in the 1980s, Atiyah and Siegel proposed the following definition, proposed the following framework, that you define a category Cobb N whose objects of Cobb N are, say, oriented n-1 manifolds, morphisms of Cobb N, Hom from M to N is manifolds W, so oriented manifolds W with boundary of W identified with M with the opposite orientation disjoint union N. So here's a picture. There's, this is my M, this is my N. N is two circles in this picture, in this cartoon picture, and M is some manifold. Up to equivalence, where equivalence is diffeomorphism relative to boundary. Okay. And composition is gluing. So for example, if you want to glue, you could glue this with this, you compose them, and this goes to this picture. That's composition. Okay, so Cobb N is, in fact, has a symmetric monoidal structure. It has a multiplication with tensor being given by disjoint union of manifolds. So here's the definition, is that an ordinary, a TQFT of dimension n is a symmetric monoidal functor Z from Cobb n to, oh sorry, I should have said here that W is of dimension n plus n. So is a functor Z from Cobb n with this disjoint union to vector spaces with the tensor product. Okay. So you could try to classify these objects. So you can ask, what's a one-dimensional TQFT given by? So classification. So in dimension one, your objects are zero manifolds with orientation. So you have the point with the positive orientation and the point with the negative orientation. And you can check, let's say the point, suppose I have a TQFT which sends the point with the positive orientation to a vector space V, then it must send the point with the negative orientation to the vector space V dual. Okay. And essentially this is the only data, because disjoint unions of points must go to tensor products. So knowing where the point goes determines everything, right? So Z Cobb 1 to vect is determined by specifying a single finite dimensional vector space. Okay. So what about dimension 2? In dimension 2, you have only the circle, which is the only interesting closed one manifold. Oh, I probably didn't say closed oriented. I apologize. So in dimension 2, the only interesting one manifold is a circle, and S1 goes to some vector space V equal to Z of S1, right? And then you can ask yourself, what do the other things, the various two manifolds give you? What structure do they give you? And so by the way, the theorem in dimension 1 should be an easy exercise. And this is a sort of harder project type exercise. If you're an undergraduate student or something, you can think of this as a kind of undergraduate project exercise, which is, so now you have the circle, it goes to some vector space V, and now you have various pictures you can draw. So you can draw, for example, this picture, and this should give you a map from V tensor V to V. If I call this manifold M, then Z of M is a map like this, which I'll call mu. It's a multiplication. Then you have this map, which is a map from V tensor V to Z of MT, which is automatically the unit, which is C. Then you have this picture, oops, sorry. This picture, which is a map which goes to a map from V to C, which is called the trace, which is Z of this manifold. Okay. And you can check that you get associativity by looking at this picture. Because this picture is homotope equivalent to this picture. This gives you associativity, and similarly, you have commutativity, which comes from the fact that this picture, okay. Similarly, one can check commutativity of mu, etc. So we have this theorem. So summing up, you can formulate a theorem that commutative Frobenius algebra, that giving a 2D TQFT, and this is, I guess, a folklore theorem. It was written down, I think, it's by digraphs somewhere. But giving a 2D TQFT is equivalent to giving a certain kind of algebra, which is a commutative Frobenius algebra. So a commutative Frobenius algebra is basically an algebra with a vector space with a multiplication like the one I've written, which is associative and equipped with a trace map and an inner product, which satisfy whatever axioms you would get by writing out the pictures here. Okay, so since I'm out of time, I'm not going to write out the full definition. You can easily look this up, the definition of a commutative Frobenius algebra. But okay, maybe I just say this is a commutative algebra. Okay, maybe I can just write it. It's a commutative algebra A. With a trace A to C, such that this inner product, which is defined to be trace of AB, is non-degenerate. That's the definition. So we have a complete classification of 2D TQFTs. But if you go to higher dimensions, Anita, can I take 2 or 3 more minutes?
Yeah, sure. Go ahead.
Thank you. Sorry for going a bit over time. Yeah. So here we have a complete classification of these things that we call 2D TQFTs. And it really comes from the fact that you can take any 2-dimensional surface and chop it up into pieces that look like the diagrams I've drawn. Right? But if you go to 3 dimensions and higher, the structure of manifolds is much more complicated. And so it's very hard to decompose a 3-manifold into pieces that are as standard as simple to understand as what we have here. So what can you do? You can say that instead of chopping up manifolds into along codimension 1 pieces alone, I chop them up into simplices, into triangles or squares or some very small objects. Then I can chop them into standard pieces. But the problem I face then is that, well, not the problem, but the price I pay is that instead of getting manifolds with boundary, I get manifolds with corners. So the boundaries themselves have boundaries and so on. So this does not generalize. So we cannot generalize this to higher dimensions because the definition is not local enough. Definition of TQFT is not sufficiently local. But all the TQFTs that come from physics, in physics, they're defined by this action principle, and the action is completely local. So you really expect an axiomatization of TQFT to encode that locality. And it turns out that the way you do that is to use infinity n categories. So, so Baud n framed is an infinity n category with objects framed 0 manifolds, 1 morphisms are cobordisms between 0 manifolds. So just intervals connecting them. 2 morphisms are manifolds with corners giving cobordisms between 1 morphisms, between 1 manifolds with boundary, all the way up to n manifolds, n morphisms, which are n manifolds with corners, framed, plus framing. I haven't said what a framing is, so let's ignore that. N manifold with corners viewed as cobordisms of n minus 1 manifolds. And after that, n plus 1 morphisms are diffeomorphisms. Well, maybe I'll just say maybe I'll just stop there. Okay, I'll just say n plus 1 morphisms are diffeomorphisms of n manifolds with corners and so on. Right, so above level n, you make everything invertible. You don't take cobordisms, but you take diffeomorphisms because diffeomorphisms are invertible. So this is a category Baud and framed, and following Bayes and Dolan, you can make a definition that let C be a symmetric monoidal infinity n category. Infinity n category with a notion of multiplication, a TQFT, an extended TQFT, framed TQFT with values in C is a functor, is a symmetric monoidal functor Z from Baud and framed to C. And again, the symmetric monoidal structure on Baud and framed is the disjoint union of all these manifolds. And here's the amazing theorem, right? So this is following, this is sort of made precise in this sense by Lurie but originally goes back to Bayes-Dolan in the 90s. And now we have the language. Thanks to Lurie, we have the language to even make this completely precise. And Lurie introduced this whole language of complete, use the language of complete Siegel spaces, etc., to make this precise. And he also proved this theorem, which is Lurie after Bayes-Dolan, after ideas of Bayes and Dolan. Is a complete classification in all dimensions that giving an n-dimensional TQFT with values in C, extended TQFT. Well, maybe we should say framed extended TQFT. Framed extended TQFT is equivalent to giving a single fully dualizable object. I haven't defined this, but so this is some finiteness condition. In C. Okay, so being fully dualizable is some generalization, like for a vector space being dualizable is the existence of this dual vector space, which pairs perfectly with it. Being fully dualizable is a really difficult and hard condition for an n category, but in any case, whatever it is, it's a finiteness condition analogous to being dualizable for a vector space. And Lurie's theorem is that giving a framed n-dimensional TQFT is equivalent to specifying a single object in this category, which has this dualizability property. So in the examples we saw in the low dimensional classification, we saw in both cases that we could classify one-dimensional TQFTs by giving a vector space, two-dimensional TQFTs by giving a single object of Rabinius algebra. And similarly, this is a kind of very deep generalization of this, which is completely independent of dimension, etc., and is completely local because you can chop up manifolds in any way you want. And so how does mirror symmetry come about? So example, if you take C to be the infinity 2 category of DG categories, of K linear infinity 1 categories. Oops, sorry. K linear infinity 1 categories, DG categories. Then you can look at TQFTs with values in it. A TQFT with values in C is determined by specifying a single object in this category, so a single DG category that is fully dualizable. Right? So this is the example that gives rise to mirror symmetry. So mirror symmetry is an equivalence of two topological quantum field theories. And those theories are determined by specifying the value on a point, which is given by a certain category. In the case of the A model, so the A model TQFT, so mirror symmetry, if you look at the Fukaya category of X omega, this gives rise to the A model TQFT. And if you look at the derived category of quasi-coherent sheaves, of coherent sheaves, I guess, sorry, that's what I said earlier, derived category of coherent sheaves, this gives rise to the B model TQFT. And mirror symmetry says these two TQFTs are equivalent. But you see the TQFT has much more information than just the, it's determined by the category, but it also has all these operations that you get in a two-dimensional TQFT, the value on the circle. So if I look at Z of C evaluated on the circle, no, not sorry, Z of C. So if, let me just finish with this. So if X is some DG category, nice DG category, nice being fully dualizable, then you get corresponding field theory ZX from Bohr to framed to DG categories. And the value of this field theory on the circle, this thing has a name. It was classically called the Hochschild homology complex, the Hochschild homology complex, sorry, Hochschild homology complex of X. And it comes with operations for every cobordism. You get operations from HH tensor X to HH, right? And in the geometric cases, so if you look at HH of dco of X for X smooth complex manifold, smooth projective, this is the direct sum of HPQ and similarly HH of Fukaya of X omega knows about, well, not knows about, is computed by symplectic homology. Compute symplectic homology. So the point is, and I'll stop here. So from the category, if you apply Lurie's theorem, you get an entire topological field theory from this higher category. And to even apply Lurie's theorem, to even formulate Lurie's theorem, you need infinity 2 categories, not just infinity 1 categories. In fact, for his general theorem, you need infinity n categories, but in the case I'm applying it, you need infinity 2 categories. And that field theory, it has in it, for example, the information of the cohomology of the space that you started with. If you start with a complex manifold, it knows about the cohomology of the space by taking the Hochschild homology, which is nothing but the value on the circle of this field theory. And these operations that you get, these operations given by cobordisms, they encode those enumerative invariants that I was telling you about that physicists were able to calculate. Right? So it's a whole long story how to construct those enumerative invariants from the category, which was only done very recently, fully rigorously after a lot of work over the last 20 years. But the point is you can recover the geometry from the field theory. And this is only the tip of the iceberg, because this is just a two-dimensional field theory. And 2D mirror symmetry is about the duality between two-dimensional TQFTs. But there are higher dimensional dualities like Langland's duality, which is and 3D mirror symmetry and so on, which involve infinity 3 categories and infinity 4 categories and so on. And it gets much harder when you go to higher dimensions. But you can still apply Lurie's theorem, which is one of the big achievements of higher category theory, to try and understand these dualities between different types of geometries that are predicted by physicists in string theory and other areas of physics. So that's the power of this technology. I'll stop there. Thank you for letting me go over time.
Thanks, Pranav, for another wonderful talk. Any questions or comments?
Yeah, I would like to ask one doubt. Hello?
Yeah, please go ahead.
Could you please go to the definition of homological mirror symmetry?
Yeah.
Yeah, here. So in that second relation, did you mean on the RHS X check and omega check?
Thanks a lot. It's a typo. Thank you very much. Oops. Yeah.
Okay, thanks.
Yeah, I should really emphasize how absolutely astounding this statement of mirror symmetry is. For mathematicians were completely blown off when physicists came around and said that there should be a space with complex parameters and scalar parameters. I mean, complex geometry and symplectic geometry get interchanged. It's just one of those things where people who are working in very different areas of mathematics suddenly realize they're talking about the same thing in different languages, right? So it's an extremely deep statement, and physicists were able to use their heuristics to come up with this, which is truly amazing. And it's also tremendously sort of, it's equally mind-blowing that Kontsevich was able to give a precise mathematical formulation of this even before this picture with 2D TQFTs and everything that I told you about existed. Like in retrospect, we can interpret it using all this stuff, but at that time it was a huge leap of imagination to say that this is how you should formulate it mathematically, and all the consequences should follow from this statement, from the statement of homological symmetry.
Yes, in the last page where you describe the Hochschild homology of the derived category of coherent shapes.
Yeah.
So what was the omega? Is it the cotangent bundle?
Yes. This is the HPQs. Maybe I should just say it in a simpler way, that from HH of X, you can produce another invariant. So this HH of X carries a circle action because it's the value, this is the value on the circle of the field theory. So rotations of the circle act on it. Okay, so that's the first amazing thing. You can only use it without the technology of infinity categories and so on. You can't even formulate the statement. You want to get the statement. So the circle acts by diffeomorphisms on itself, and so it acts on HH. So from this, you can take the homotopy fixed points of the circle action. This thing is called cyclic homology. Okay. And the cyclic homology, from the cyclic homology, you can produce something called, I don't want to define it precisely. It's not hard, but maybe people will get bored. From this, you can produce something called HP of X, which is the periodic cyclic homology. And basically, yeah, okay, so I won't give the formal definition, but it's just some easy algebraic construction applied to cyclic homology. Now, if you do HP of the derived category of coherent sheaves, when X is, say, smooth projective, then this is just the two periodic Derived homology of X. Maybe that's, maybe not everybody knows HPQ from Kähler geometry, but Derived homology is, just the usual Betti numbers. So you can recover the Betti numbers of the space, for example, by using this 2D TQFT to construct, all you need is the Hochschild homology. So that existed before 2D TQFTs. But what you really use the 2D TQFT for is to define this quantum product, this product on Hochschild homology, which gives you the quantum deformed cup product after doing some work. And that encodes what's called the Gromov-Witten invariants, which are these enumerative invariants that we were interested in to start with. So that's the motivation.
Thanks.
So this was just supposed to be like a motivation to say that, why do we care about these infinity n categories? We care about them, one big theorem. People often ask, what's the big theorem you can prove using this? One very powerful theorem is this cobordism hypothesis, this classification of TQFTs in all dimensions without any hypothesis. And it gives you a systematic way to understand all these dualities that people in string theory predict, whether it's Langland's duality or mirror symmetry and so on. They all fall under this statement that there are two TQFTs that are equivalent. And when you interpret it like this, you find some statement that some category is equal to some other category somewhere else from a different area of mathematics.
Any other questions? Okay, so if no more questions, then let us thank the speaker. You may wish to unmute yourself and clap, or you may wish to type in the chat box. So just one word with the audience. If you do not belong to ISI Bangalore and wish to receive notifications for similar online lectures in future, then either drop me an email or keep an eye on this researchseminars.org. And this brings us to the end of this series of lectures. Thanks, Pranav. Thanks once again. And
thank you so much. Thank you.
so goodbye and take care.
Bye-bye.
Bye. Bye.
Thank you.